Now here we go for exercise 7.4, but before I start 7.4 we discuss here integral of this type 1 upon quadratic. Integral of the type inside the integral you have 1 upon quadratic expression, 1 upon quadratic. It may be 1 upon inside the square root quadratic expression, right? Inside the square root quadratic expression, with or without quadratic. Procedure is same, formula would be different at the end, remember. Or we may have integral of the type linear upon quadratic. So in the numerator you have linear function like this, ax plus b, and here you have some quadratic expression with or without square root. So here linear upon quadratic, you may have here ax square plus bx plus c like this. This is linear. Let me write here capital A, capital B and capital C. You may have with square root or without square root, remember. That's not important. Procedure is same. So either this type of the integral, linear upon quadratic with square root, this is without square root, or just 1 upon quadratic without square root with square root. So let's see by an example. I'll tell you how to do this. For example, I have this question is find this integral. Find integral of 1 upon, let me write for example x square plus 2x plus, let me write here 7, such integral. Now this is 1 upon quadratic. Now here in integration we use this, every quadratic can be expressed as sum of the difference of the two perfect squares. So x square plus 2x, what should be the last term? That is 1 here to make it perfect square, plus 6. So this would be x plus 1 the whole square plus root 6 the whole square. Every quadratic can be expressed as sum or the difference of the two perfect squares, right? So we express whether it is this quadratic or this quadratic as a sum or the difference of the two perfect square. One expression here plus or minus the other expression. We'll do this. Every quadratic can be expressed as a sum or the difference of the two perfect square by just rearranging last term. How do we get this last term? This is the formula you might be knowing. LT, last term, equals to coefficient of the middle term, 2 here upon 2 always, and then whole square equals to here 1. So that's why I wrote this. Last term equals to coefficient of middle term by 2 the whole square. You might have studied earlier. This is the formula for last term. So what I did basically, I have expressed this quadratic as a summation of the two perfect square. This term should be constant. Every quadratic can be expressed as a sum or the difference of the two perfect squares. So here perfect square, here perfect square. Okay, so after doing this, now we have here 1 upon, instead of this I can write x plus 1 the whole square plus root 6 the whole square. Now you recall this is one of the known formula. Which formula? X square plus a square. Can you recall what is x square plus a square? We already stated earlier. If you just recall, it is 1 upon a tan inverse x by a. 1 upon a means 1 upon root 6 into tan inverse x means x plus 1 by a, that is root 6 plus c. This is your answer. Which formula have used? This one. Integral of 1 upon x square plus a square that is equals to 1 upon a tan inverse x by a, if you remember, plus c. Here remember, this is a linear function, so I could consider these as x. So this is your answer, x square plus a square. One more example, let me see here. Suppose I have next one with square root. So 1 upon, suppose inside the square root I have, let's write 4x squared plus, let me write here 2x plus, let's write 7. Inside the square root you have quadratic. What is the procedure? What I told you, every quadratic can be expressed as a sum of the difference of the two perfect squares. So this quadratic we are going to express in this form. So what I'll do is, here you can do directly also, I'll take coefficient of x squared equals to 1. So to make it coefficient of x square equals to 1, I'll take 4 outside. If I take 4 outside, it will be 1 by 2. Now inside the square root, what we'll get? This is x square plus 4 by 2. So it is 1 by 2x plus 7 by 4. I hope this is clear to you. What I did, if you want one step extra, inside the square root keep 4 outside. So x squared 2 by 4, 1 by 2x plus 7 by 4 here. Taking just 4 outside here, and then taking 4 outside the square root becomes 2. Now, as I told you, what I did, you must have realized, I have expressed given quadratic in such a way that the coefficient of x squared becomes 1 here. Now here, what's the coefficient of middle term? 1 by 2. You square, you do half of it, so it would be 1 by 4 and then square. So it would be like this, x squared plus 1 by 2x. Here half of this, 1 by 4 and then square it. So 1 by 16. I'm adding this. So here 7 by 4 minus 1 by 16. How I got this? This one, 1 by 2, half of it and then square it. This is the last term. Last term equals to 1 by 4, the whole square, 16. Adding this, subtracting this. Adding and subtracting this much. Now this would be the perfect square, remember. So 1 upon 2 here. Over here, x plus first 3 terms, 1 by 4 the whole square. Simplify this much. So I need to take 16 as LCM here. So by 16, so here 4, 28 minus 1, so 27. Here also dx, remember. So finally here, you are getting like this. If I just rewrite, you can do directly also, but let me write one more step. X plus 1 upon 4 the whole square, root 27 by 4 the whole square. Now it is one of the standard formula, 1 upon root of x square plus a square. If you remember, log of mod of, this is linear function, so you can imagine this as x, log of mod of x plus the same expression, that is x plus 1 by 4 the whole square plus 27, same expression means 27 by 16 plus c. Which formula I've used? I'll just show you. I've used this formula. This one I've used. Integral of 1 upon root of x square plus a square. What's the integral of this? Log of mod of x plus the same expression, that is x square plus a square. I've used this formula. So here x means this much. So you have this. Now further, if you want, you can simplify. 1 upon 2 as it is, log of x plus 1 by 4 as it is here. What is this? This is nothing but actually, if you go back, this comes from this, which is from this, which is from this. So you can write this one directly. So I can write here root of x square plus 1 by 2x plus 7 by 4. This is your answer finally. I repeat, from where I wrote this, from this comes from this, which comes from this, and which comes from this basically. Not this one, this is different, remember, up to this, because I have taken 1/2 outside. So this way you need to do if you have quadratic expression with square root. Okay, now next one is we want to do such questions. Linear upon quadratic, linear upon quadratic, linear upon quadratic. So there we have the following two steps. So let me do this now. We want to do such questions. Linear expression upon quadratic expression. Upon quadratic. You may have with or without square root, remember. You may have square root or it may be free from the square root. So there are two steps. The first step is here. Set the derivative. This is step number 1. Set the derivative of denominator expression, denominator into numerator. Denominator expression into numerator. So you set the derivative of quadratic over here. That's a step number 1. I'll take an example so you'll realize. What is the first step? Set the derivative of quadratic over there. Denominator over numerator, number 1. Number 2, split into two integrals. Split into two integrals. So immediately you'll realize then how to proceed. Split into two integrals. So then after doing this here, the one of the integral will be f dash upon f because you have set the derivative, and the other one is just constant upon quadratic, and this can be integrated very easily. Constant upon quadratic. This you know, this is log of mode of denominator expression, and this is constant, you can take it outside. This is 1 upon quadratic, that I already explained. So all linear upon quadratic questions should be taken care with this procedure. Right, this is a standard technique, remember. Set the derivative, split into two integrals, and then immediately it reduced to the previous technique. For example, here, whether it is with square root or without square root, procedure remains same, remember. Formula might be different here. Okay. So, for example, suppose I have, let me write like this here. 2x square plus x plus 1. For example, I have this. Let me write just x square plus x plus 1. Okay. And here I have, let me write just x plus 1. Okay. So this is which type of the question? Linear upon quadratic. Which type of the question? Linear upon quadratic. Now what's the first step? Derivative of this you are going to set here. What's the derivative of this one? Your derivative of this expression is 2x plus 1. So I want to set there. Now I need 2x. I cannot write x plus x. Normally variables should not be added. So to get 2, I'll multiply and divide by 2. So it would be 2x plus 2. That the plus 2 can write plus 1, remember. What I did? Multiplying and dividing by 2. So here 1 by 2 as it is. Here I can rewrite 2x plus 1 plus 1. So what I did? I set the derivative, remember. Step number 1. Set the derivative of denominator into numerator. So I have set the derivative. This one. Then split into two integrals. So I'm splitting into two integrals. So 1 upon 2 here. This upon this, that is 2x plus 1 upon x square plus x plus 1. Half is already there, half outside. This is nothing but 1 upon x square plus x plus 1. Have you realized now? That's what I told you. The one integral will be f dash upon f. You see, this is f dash, this is f. So you know how to integrate this. F dash upon f, log of mode of denominator expression. And how do we do this? This we already discussed. So this is 1 upon 2. This is f dash. This is f. So log of mode of denominator expression. Plus, now this is 1 upon quadratic. Well, how do we handle 1 upon quadratic? You know procedure. Express this is sum or the difference of the two perfect squares here. So this is 1 upon x squared plus x. How do we get the last term? Here LT equals to coefficient of the middle term 1 upon 2 always the whole square. That is 1 by 4. So last term should be 1 by 4. I am adding 1 by 4. Plus 1 is there. So I need to write minus 1 by 4. Adding and subtracting 1 by 4. Why I did this? Because I want to express this is a perfect square, remember, by finding this last term. Okay, so now finally we are getting this one 1 upon 2 here, 1 upon 2 log of mode of x square plus x plus 1 half here 1 upon x plus 1 by 2 the whole square plus simplification of this much. What is this? 3 by 4, that you can write root 3 by 2 whole square. Fine. What is this? This is nothing but, this is nothing but 4 minus 1, 3 by 4, that is root 3 by 2. So here 1 upon 2, this one as it is. Now you can see that this is a known formula. Which formula? This is linear function. You can imagine this as x square plus a square. What is that? What is x square plus a square? 1 upon a. A is root 3 by 2. Tan inverse x by a. X means x plus 1 by 2. Upon a, that is root 3 by 2 plus c. 1 by 2 as it is. 1 upon a tan inverse x by a. So here this one as it is, you can just copy it. This 2 will goes away. This is just 1 by root 3 tan inverse here. You have 2x plus 1 upon root 3 plus c. This is your answer. So this way, it might be a little bit lengthy, but it's not difficult. Remember, steps you need to keep in your mind. What is the first step? Set the derivative. So I've tried to set the derivative. What's the second step? Split into two integral. One would be known to you, the other one would be 1 upon quadratic. Fine. Okay. So before I go to exercise questions, sometimes the same question can be done like this. I'm doing let me take the new question instead of taking the same question. So let's see this question now. You have linear upon quadratic x plus 2 upon 2x square plus 6x plus 5. What I want to do? I want to set the derivative of this one over here. So one way is this. What I'll do, instead of this, x plus 2 equals to derivative of this into some constant. We'll find that constant. What's the derivative here? 4x plus 6 plus some another constant b. This is also standard technique, remember. What I want to do, instead of this, I want to set the derivative of this one plus some constant. So instead of this here, x plus 2, I've written some constant a into derivative of this expression plus some another constant. Okay, now what we do, we just compare the coefficients and we find a and b. So x plus 2 equals to here 4ax plus 6x plus b. Fine. Now compare the coefficient. What's the coefficient of x here? 4a. What's the coefficient of x here? 1. So 1 equals to 4a. 6a plus b equals to constant 2. This is constant. Comparing constant with constant, comparing coefficients of x. 4a, here coefficient of x is 1. Okay, so what is a from this? 1 by 4. Put a here, so we'll get the b. So 6 into 1 by 4 plus b equals to 2. So therefore b equals to 2 minus, this is 3 by 2. 3 by 2. So you will get the b equals to 4 minus 1, that is half. So 1 by 2. So you got a and b, right? So therefore finally, instead of x plus 1, you have this expression with values of a and b. So I'll come to I means given integral. This integral. What is x plus 2? That is a. A is 1 by 4 into derivative. What is that? 4x plus 6 plus b. What is b? That is half upon the quadratic expression. This way also you can do, or you can do trial and error directly also, remember. What is this? This is step number 1. Set the derivative. So I've set the derivative. You can just simplify this. You can verify. If you simplify this, you will get exactly x plus 2, remember. What we did nothing. Just instead of x plus 2, we have set derivative plus some constant, remember. Right? Through this procedure. I hope this is clear to you. Okay. You can verify. I'm showing. If I open this bracket, you see x, if I open the bracket, plus 6 by 4, which is 3 by 2 plus 1 by 2. You can see that this is again x plus 2, the same expression. So this is just x plus 2, rearrangement. Now split into 2. So 1 upon 4 being constant outside. This is 4x plus 6 upon 2x square plus 6x plus 5, the dx. This is f dash upon f form. Plus here 1 by 2 will come out. And this is 1 upon 2x square plus 6x plus 5. Right. This you know, f dash upon f, log of mode of denominator expression. How do we do this? This is 1 upon quadratic. So express this quadratic as the sum or the difference of the two perfect squares. Right? Just I wanted to show you that this linear upon quadratic expression, if you are given, you can express numerator in form of derivative like this. You can do directly also, remember. See, I'm doing directly if you want to show, if you want to see here directly without using this AB. If you feel that this is easier, you can do it. You need to keep derivative of this one in your mind. What's the derivative of this one? That is 4x plus 6, right? Derivative is this. I want this one in the numerator. Now I need 4x. So multiply and dividing by 4. I'll start with x plus 2. Multiply and dividing by 4. So what I'll get? 4x plus 8. Fine. But I just need 4x plus 6. So 8 I'll rewrite like this. 8 I'll rewrite like this. I need just 6. So 6 plus 2. Instead of 8 I wrote this. Now you keep this as a one term and this as a separate term. 1 by 4. 4x plus 6 plus 1 by 4 into 2. So what you are getting? 1 upon 4 into 4x plus 6 plus 1 by 2. So you see, you are getting the same thing. That's what you are getting here. Same. This was x plus 2, you see. So you can do directly like this or using a B technique. Whichever way you like, you can do it. Right? But this should be done without a mistake, remember. Here mainly we use the following formulas. Let me just remind you. The one is this. We already discussed this. Just to remind you, if you have 1 upon root of, let me write x square plus a square. It is given by, you know, log of mode of x plus the same expression plus c. Integral of 1 upon root of x square plus a square. If you have even minus here, this is 1 upon root of x square minus a square the same formula, log of mod of x plus the same expression, which is x square minus a square plus c. Log of mod of x plus the same expression, log of mod of x plus the same expression. Okay, one is this. Second one, here you know this, if you have like this, a square minus x square, right, inside the square root, you must see the difference between these two. Remember, here variable first, answer is in form of log, here constant first, at both the places your square root, so here answer is in form of sine inverse x by a plus c. If you put a equals to 1, it just becomes, if I take a equals to 1 here, this is a known integral, 1 minus x squared. This is a derivative of which function? Sine inverse. So integral is sine inverse x plus c. Just putting a equals to 1, you are getting this. Difference between these two must be noted. Here variable first, here constant first. Okay. And third one, which we'll use here, that is without square root, x square plus a square. It is given by 1 upon a tan inverse x by a. Remember, 1 upon a tan inverse x by a plus c. 1 upon a, in the formula of sine inverse, you are not having 1 upon a. 1 upon a is not there, remember, in the formula of sine inverse. In the formula of tan inverse, you do have 1 upon a, remember. 1 upon a tan inverse x by a. If I put a equals to 1, a equals to 1 plus x squared dx. What is this? This is tan inverse x plus c. Differentiation of this portion is this. Here also you can verify. So mainly we use this formulas here. If you put square root here, it becomes the first formula. You see, if I put the square root, it becomes this formula. And if you have inside the square root variable first, answer is in form of log, constant first, then answer is in form of, remember, sine inverse. Okay, so with this information, now we go to next exercise, which is 7.4. Substitution would be there, remember, that is fundamental technique. So that can be used here. And what else we have used here? Remember, every quadratic can be expressed as what? The sum or the difference of the two perfect squares. That is, we have used here effectively. If you have quadratic here, that can be expressed as a sum or the difference of two perfect squares. This can be done, remember, every time, and that's what you are going to do here. Any quadratic can be expressed. And what's the formula for the last term? That is coefficient of middle term by 2 the whole square, right? With the help of this you can do this. And which two types of the integrals you have studied? Mainly 1 upon quadratic. What you are going to do? Quadratic you are going to express as the sum or the difference of the two perfect squares, and then use one of the formula. Or you may have inside the square root quadratic. Procedure is same, at the end formula might be different, remember. And which second type? That is linear upon quadratic. Linear upon quadratic, with or without square root. How do we do? Linear upon quadratic. So there what we do, there are two steps as I mentioned. Step 1, set the derivative, and step number 2, split into two integrals as I explained earlier. You do this, right? That's what we are going to do in the next exercise. The next entire exercise is based on this concept, remember. Exercise 7.4, first question. Question number 1 here, that is integral of 3x squared upon x raised to 6 plus 1 dx. Now you must have realized numerator is derivative of x cube. So I can rewrite x raised to 6 as cube n square. So we are going to put x cube equals to t here, substitution. What's the differentiation of this one? 3x squared equals to dt by dx. I'll write dx over here directly. So now you can see that this is there in the numerator this much. So that become dt. So the integral reduced to here dt. This is just 1. 6 you can write cube n square. So square plus 1. Right? This x raised to 6 is actually x cubed the whole square. Now this is t, so t square. What is the integral of 1 upon 1 plus x squared? You know it is tan inverse t. Tan inverse t plus c. But what is t in turn? That is nothing but the x cube. So this is a required integral. Substitution, remember. Question number 2 here. If I write second question here. Question number 2, integral of 1 upon root of 1 plus 4x square. This is directly quadratic expression with the perfect squares of two expressions. So you can rewrite like this here. 1 squared plus 2x the whole square. And this is linear. So this is like a root of x squared plus a squared. X squared plus a squared. So what's the integral? Log of mod of x. X means 2x plus the same expression, that is 1 plus 4x squared upon the coefficient of x, which is 2. Remember what you did, you had considered 2x as x, remember here, because we have the formula that is just for x only. We have used this formula, remember, the first formula which I have stated here. I've used this formula, this one, remember. This one I've used. So here, instead of x, you have 2x, remember. Log of mod of x. X means here 2x plus the same expression, means this expression or this expression. Now when you consider 2x as x in linear function, upon you need to write its coefficient. So its coefficient is what here? 2. So finally 1 upon 2 log of mod of 2x plus root of 1 plus 4x squared plus c. Here also plus c, remember. Fine? Okay. Now question number 3, third question. Integral of 1 upon root of 2 minus x the whole square plus 1 square dx. Now you can see that this is already in the perfect squares form. This looks like which form? X square plus a square with square root. This is linear function. You can imagine this is x. So same formula what you have written here. This is x for us. So what's your answer? Log of mod of x. X means 2 minus x plus the same expression. Same expression means this one, 2 minus x the whole square plus 1 square plus c. Remember, don't forget to write the coefficient of x. What's the coefficient of x here? Minus 1. So upon minus 1. So finally we are getting minus log of mod of 2 minus x plus 2 minus x the whole square plus 1 plus c. Which formula? X squared plus a squared. Log of mod of x plus the same expression upon the coefficient of x, which is minus 1. So upon minus 1, which I wrote here. So we have this. Okay. Question number 4 now. If I go to fourth question, let me write that. So in the fourth question, you see here, integral of 1 upon inside the square root 9 minus 25 squared. You see inside the square root you have constant first. You know that if you have constant first, answer should be in form of sine inverse. So I can rewrite like this: 3 square minus 5x the whole square dx. Here also dx. This is which formula? A square minus x square. If you have a square minus x square, your answer will be in form of sine inverse. A square minus a square, constant first, answer is in form of sine inverse. So here your integral would be sine inverse x means 5x, by a, that is by 3, upon the coefficient of x, that is I will write 1 upon 5 in front of this plus c, remember. Why I wrote upon by 5? Because there I have considered 5x as x, so I need to write upon the coefficient of x, which is 5. Here you see upon the coefficient of x, which is minus 1. When you consider linear function as x, here I have considered this as x. Always you need to write upon the coefficient of x. So 1 upon sine inverse x by a upon the coefficient of x, which is 5, remember, not minus 5.